So welcome to part 3 of inventing sequence models as vectorized signal processors. And just to recapitulate the abstract, we're inventing these things from basic ideas as a way of just hopefully understanding them better, maybe coming up with an explanation of some of the things that are going on, and to just foster a blend of ideas. So in reality, it was a blend of principle and empiricism, right? I mean, the models did way more than anyone expected. And so I don't think anyone really understands everything that goes on in a large language model, for example. But we could have invented the structures from various understandable points of view. And that's kind of the basic theme of what we're trying, what I'm trying to do with this. So, so the advantages are, since I'm coming from the point of view of signal processing to a signal processing person, it's a very quick update on what some of the structures are. And for machine learning people, I'm hoping that it's an interesting signal processing point of view. Just get some signal processing insights into some of these structures, and maybe that'll be helpful. And it also just comes up, there are all kinds of suggestions of what to try. In other words, if these ideas for how you would invent these structures are reasonable, then they suggest ways of improving them, and so those could be tried. And if it doesn't improve them, then it means maybe that's not what was going on. Okay, so then we went through the basic idea. So the basic setup was start with a one-pole filter. Here's the diagram of a one-pole digital filter. It's got a feedback coefficient P, that's your pole for your one-pole filter. And then you have an input gain, which is normally 1 minus P to get unit amplitude peak gain. And so Z inverse here denotes a delay. You can also just imagine D there. And this is a linear time invariant filter. It has a transfer function, but it's going to get nonlinear very soon, right? Once these coefficients are learned as a function of the data, then it becomes a nonlinear filter, and it doesn't have a transfer function anymore. Z inverse is okay because the delay is still a delay, so we can still call a delay that, but it's no longer something we can treat as a linear time invariant system. So here's the difference equation. This is what you write in code, and then here's your transfer function for analyzing it. So you see your gain G and your pole P. And so this is just kind of what we do in a beginning signal processing class. And so the thought experiment is, let's do a project where we're going to make an associative memory out of this one-pole filter. So our input will then be a long vector. And so capital N here is the model dimension in machine learning speak. And it can represent anything we want, any kind of label. And we'll just start out with the gain being 1. And writing little underbars indicate that everything's vectorized. So the input is no longer just a single sample. It's a vector Rn and Rn. And then G is a vector of 1s. And P is a vector of 1s. And so it's basically just getting rid of them. And so that means then that the output Y is just a sum of all the inputs. And so that's a digital integrator. And it's not leaky, meaning that it just keeps growing. The vectors just keep piling up in there. And so the idea is that that's going to be our memory. And then we can retrieve the vectors using the inner product. And so we'll choose the dimension n so large that the vectors are mostly orthogonal, so that an inner product will be able to retrieve them without a lot of interference. And so in order for this to be an associative memory, we want the vectors to be from an embedding that's reasonable, like word to vec, where closeness, geometric closeness is similarity in meaning. So similar words are located similarly close together in the space. And so that's the basic setup. And so let's see what we can do with this. So given the sum of vectors, we can have a query vector, and then we can take an inner product with the sum and see that it picks out the vector element, the component, the vector in the sum that is similar to the query will have a large inner product. And so by linearity of the inner product, you have a kind of superposition. And so you get the sum of all of the inner products, and and so the biggest one will dominate and exceed your threshold, and then you say, okay, well, I think that's probably there. And it's especially ideal if the other vectors are substantially orthogonal, in which case you don't get a large contribution from any other vectors. And so you really do just get mainly that one term that you're looking for. And so this looks like a perceptron. And so we talked about this already. I'll just go through this quickly. So we talked about how this suggests that you might want to reserve the radial dimension for similarity scoring. And so you would then normalize to the hypersphere, and that's RMS norm. And instead of setting the norm to 1, you can set the norm squared to n. And that's kind of a nice normalization because it means your coordinates have unit variance. So that's kind of a nice numerical choice. That's what Anthropic does, at least in the papers I was just reading. So this is a new thing I added. So yeah.
Yeah, a quick question on that. Associative memory. So what you get out of this is a signal, yes, I've seen this input before. It doesn't look up a value. Is that correct?
Yeah, it's just detecting. It's signal
Detecting
detection.
that
Yeah,
you've seen
vector
pattern before.
detection.
Okay.
Yeah, you get the sum, and then you say, query, is this vector W in your sum? And so the inner product will basically, by linearity, fire on that vector if it's in there. So the kth vector, if that's in there, will fire this inner product, and you'll get the norm squared, and that will exceed your threshold. And all the other vectors are substantially orthogonal, and they don't add a whole lot to this. That's the idea. That's the basic approximate idea of the memory and the retrieval. And this is, reasonably what's going on in a perceptron, where your weights are your query vector, and your input is some pattern, and the weights are the pattern that you're looking for. And so the optimal detector for signal and noise is an inner product. That is a well-established signal detection thing that goes back to the 1940s, probably, if not earlier. It's a very classic theory of detection of signals and noise. Van Trees was the classic book on this kind of stuff. And so the signal detection and noise problem is, it can be thought of as the source of this kind of approach. And so it really does map. It's a nice correspondence to, a pretty classic problem. And so this idea that we want to set the threshold independent of the vector, we don't want it to depend on k, motivates normalizing the vectors. And so it's one way of motivating RMS norm. And I just think that's interesting. It does not motivate layer norm, which was, as far as I know, that was used first. So, first there was no normalization, then there was layer normalization, and then RMS norm kind of took over. And I think that's where we are now. RMS norms quite often seen in these architectures. And this is just one way to get there. It's just one way to arrive at it. And it has other implications. So then this is the thing I added, which was to put in a forgetting factor. So it's for like RNN style memory. So, an RNN has one hidden state vector, right? So that's your memory. That's everything that the RNN knows is just in that one vector. And it's an exponentially fading sum of all of the inputs that have come in. And here they are. So this is linearized, right? So you have the sum of inputs, and it's being weighted by P again. P is our pole. It's our forgetting factor. It's our feedback gain of 0.99 or whatever. And so this is just an expression for the output at time n, looking from time 0. So you sum from time 0 up to time n, and then your forgetting factor is, P to the n minus m, where m is the current index here. So for m equals 0, it's P to the n, your maximum forgetting. So that's, n samples ago. But at time n, it hasn't even done anything yet. So it's just the input just comes in straight to the current time, but then all previous times fade into the past exponentially. So that's your classic recursive forgetting factor sort of thing. And that's what RNNs have, at least when the feedback gain sits still. If it just freezes, then it looks like this. And so now we, but I just want to look at the difference in the retrieval in this case. And so let's say we have a query vector W, and we take the inner product and we run it in there. We find that instead of the norm squared of the signal, or the vector that's there, which now we've normalized to 1, we get the forgetting vector to the n minus k power. And that's decreasing as we go through time, right? So it depends on how many samples it's been applied, but as n goes to infinity, this gets driven down to 0, and it will eventually go below our threshold. So it limits our memory. So the threshold, or the bias, so to speak, sets an upper limit on how much time you can be accumulating these vectors. I thought that was interesting to look at. And let's see, let's see where. Yeah, I get it. Okay, I was just wondering why this k. It's because we're at the kth position here in this sum. That's just where it came out. Yeah, okay. That all right. I'm going to return to that, I think. Okay, so B is the detection threshold, and it's independent of k if we have a normalized vector. And so we see that we have to watch out. It'll decay below the bias and not fire. And so it sort of sets an upper limit on n. And so if you want to have a particular forgetting factor, then you get a bias to the 1 over n as your bound. But it's not a bad one. I'll show you some examples. And so you can say then that the maximum time that you can look back in time is the log of the bias divided by the log of the forgetting factor. And that's just, solving this inequality, taking the log of both sides. So I thought that was interesting to look at. Yeah?
Yeah, another quick question. So when you have that decay in there, then does that mean that kind of the weights are not, they're moving up the unit hypersphere, right? As they decay.
Yeah.
So you're it's kind of blending or overloading similarity, which is the magnitude, as well as this kind of age signal.
Yes, absolutely.
Okay. Is
Right.
Can you do those separately, do you think, somehow?
I think so, yeah.
Okay.
Yeah, I thought about this a bit, and I think that what I want to do is not have a forgetting factor. So, in my experiments, I plan to have p equals 1. So you never have an exponential fading memory. Instead, you just have resets. So in other words, it's a little bit like the old LSTM idea where you just have a kind of an activation, but you have to be really careful with it to preserve stability, avoid vanishing and exploding gradients. But I do think that makes a lot more sense, that you're either accumulating memory or you're trying to clear the memory. That's kind of how I want to think about it. And then you don't have that conflation of age with the similarity. So when you get a small inner product, there's no difference between it just being an old vector and a very different vector. They do the same thing. So it's a conflation that we can avoid.
Right. Can you imagine so that's a clear memory based on, I've got a new X and I want to remove it from my memory. Is there a way that you can imagine something that forgets memory because memory's full? If I overload too much into memory, it's full, and everything starts getting noisy.
Yes.
Is there a way to somehow clear that?
Yeah, there is. We call them truncated IIR filters. And so the way it would work is that you have to have a kind of a side memory that's just shuffling things along. And so what happens is let's say P is equal to 1. So it's really going back to our previous just a sum. Then what you do is you have a delay line that has a copy of all the inputs up to time, the time that you need, and then you subtract it. So you subtract from the sum the vector that you don't want anymore. So you just add another term out here, which is subtracting the, so maybe it's like m equals 0, you could subtract that one, and you could subtract x0. And then what you do is create a sliding rectangular window that way.
Right. Okay.
And then in the TIIR world, they have this really neat trick where it turns out not to really work that well in practice, because you're doing an integrator that just keeps summing and summing, and so round off noise is growing, right? The round off error has a linearly growing variance, and so when you subtract off the oldest members of the memory, it doesn't go away. So you don't subtract the round off error, and it just keeps growing. So you have to do some kind of reset. And so the trick there is that you have two of these systems and you ping pong them. So let's say your desired memory length is capital M, then you grow up to size M and you start subtracting, and then you grow another one. And then after capital M samples, they're theoretically identical, but they're not exactly identical because round off errors and such. But you can then clear one of them and switch to the other one, and then let it run for a while. And when its round off error starts to be a problem, then you start another one. You start growing another one, and after M samples, is theoretically identical, but not really because of the round off error. And then you switch to it. So you ping pong between these two systems that, so they've never really been, going for more than 2M samples or however you set it up. You really can wait a while. It depends on your situation, but, you can really kind of do it infrequently. Once in a while, you can fire up another one. So that's the subject of TIIR filters, truncated infinite impulse response filter. And I do think that's applicable here. That's one of my papers that will probably never get finished. I've actually got a partial write-up on that, believe it or not. So I can send you the partial PDF.
So can you think of a signal processing way of doing it where it's not a sliding window? In other words, the age of the vector isn't the criteria that says I need to forget it, but some measure of importance. I just want to forget the unimportant stuff, not the stuff that's outside the window.
So it's more like gating.
Yeah, somehow. Not quite sure how,
Well,
but yeah.
Well, I think that the way the RNNs do it nowadays is with a learned feedback coefficient, like Mamba, it's a feedback coefficient that is a function of the input, and so when the input is the word then it just clamps down. And in Mamba, it does that by giving you a very large delta, I think it is, and then that drives the feedback coefficient down towards 0, or maybe it catches it at the input. There's an input projection as well. So there's two places I think where it can get rid of those words. So you basically just don't let it in there. And
yeah, just so you can stop. If not important, don't remember it to start with.
right. Yeah,
But
either doesn't make it into the memory, or it can't feed back around.
right. Or if it's somehow measured as not important, then purging it, which maybe should be two different things.
And what I think would be really nice is, yeah, I definitely think they should be separated. And what I think would be really nice is having the feedback coefficient, trigger a reset, basically go to 0. It manually adjustable things like punctuation, like end of sentence punctuation, or end of paragraph, a blank line. There are things that you could define as very well defined, very reliable reset signals that, I'm just doing a word embedder here, or a sentence embedder, or a paragraph embedder. And so I have a very well-known reset algorithm here. And to make it really fancy, you could have a very nice neural segmenter, that recognizes end of sentence in a very sophisticated way, and can do either semicolons or period, and it can distinguish between abbreviations and end of sentence, all that kind of stuff. And so you could drive it with that. And to me, building up something manual like that is very appealing, because then you understand it, you know exactly what it's doing, And that's more like my world, where you build things that we really understand. I'm sort of trying to claw my way back to that world, is if at all possible. So let's see. Yeah, this is exactly, I think, a real issue that can be addressed. Disentangling age from distance. Okay, so there's this trade-off here that if you lower your threshold, you can get more memory, but you also get more false detections from interference. And I also did a new calculation on that. So the one that I talked about before was orthogonality in high dimensions, and it just takes you through the basic calculation that if two vectors, you take two random vectors that are unit norm in n dimensions and take an inner product, then the expected value of the inner product squared is 1 over n. And that's nice because it's nice and small. And so that we used to make some suggestions, and we went over those previously. And so, but this is something new here. I mean, it's not new, but it dawned on me that, well, wait a minute, we've got other vectors here. So we've got a lot of interference. So, we looked at the inner product of two random vectors. Well, what we really have is a random vector, say, and a sum of random vectors. And so when you work out the calculation on that, then it's not 1 over n, it's n over n. And this is obvious when you think about the fact that variance grows linearly in a digital integrator like that, right? So of course that's got to be right. So, but that means we can only go capital N, that the model dimension. When we get to the model dimension, then our expected inner product squared is the same as noise and signal become equal. That's the basic problem. And so retrieval will become unreliable when the number of summed vectors nears the model dimension. So that was something that should have been obvious. I should have mentioned it, but now it's obvious. Okay, so, and now n is, of course, the magic number of how many orthogonal vectors you can have in n dimensions. And so it's kind of elegant in that sense. So, so it kind of leads you to want to think in terms of how many vectors do I really want in that memory? I'm going to do careful gating, as you're talking about. And I'm going to only have some smaller number, L. So I'm going to have, so the size of my memory is going to be significantly less than the model dimension. And then this effect means that we can still detect reliably. So that seems like an important thing to have in mind. So, and so then I thought, well, how many do we really need? And so I thought, well, really, I can only remember about 7 things, right? So, so phone numbers, are 7 digits because of how limited our short-term memory is. AT&T did the research and determined that 7 was pushing it already. And so these are unrelated numbers. You have to just remember, but it's really 3 plus 4. So it's not 7 really. It's 3 and 4. So I would claim that you already have 2 levels of hierarchy, or at least 1 level. I don't know how you say that, but it's not 1 set of 7. It's 3 and 4 things. That's a group of 2 things, 3 and 4. So I think that's very significant. So my question then becomes, can language be parsed using 7 vectors or less at each level? And this fits pretty well with the original transform. It had 8 attention heads and 6 layers, like the neocortex. So it's kind of in the right ballpark in terms of, the sizes. So, so here's just kind of a thought experiment. So you got 26 characters. Let's say you have to make all of your syllables in 7 characters or less. That's no problem. Let's say you have to make your words in 7 syllables or less. That's pretty good, except for supercalifragilistic and such like that. And then you have, and then you can have a noun with up to 6 modifying adjectives. Take that in one gulp. That seems reasonable. A verb with up to 6 adverbs, gulp. Then you can start having a whole noun phrase. You can start having a direct object or an indirect object, a prepositional phrase. Then you can have sentences, right? Subject, verb, maybe an indirect object and an object. and then you can get up to a sentence, and then, you know, any kind of sentence, and then paragraphs, and then a section. And, you know, paragraph would be less than 7 sentences. So my writing style guideline is now no more than 7 sentences in a paragraph, no more than 7 paragraphs in a section, no more than 7 sections in a chapter, and 7 chapters. And if you want people to really be able to take it in, right? So I don't know, it just seems like a reasonable guideline. And then how many subject areas, you know, are there? And so now if we only have 6 layers in our neocortex, then we're gonna have to, like, to get, you know, 15 layers plus, we're gonna have to, you know, have like some of them over here, and then project around and go through it again. So you have to go through more than one stack in the neocortex. And of course, we know we have specialized neurons for speech. I don't know anything about it. What is it? Is it called Broca's area or something? Anyway, there's part of the brain that specializes in speech, and whatever's going on in there, I don't know. But if you were doing it in the neocortex, and you would have to go through it multiple times. And so so I have this nice little illustration of, these are sentence diagrams. It looks like that was it, actually. Anyway, it can, so this is something I found. I have to open it up here. Where did I open up an ad, didn't I? Here we go. So this is, so if you diagram a sentence, you know, the question is, do you ever have more than 7 things hanging off of a line? So this is, I think everybody's probably done sentence diagramming. The responsibilities of a bookkeeper, which are too numerous to list, can be sometimes heavy, but, you know, so you've seen this sort of thing. So it's this kind of hierarchy that can sort of keep your memories down to 7 things or less, right? If you just, here's a really complex example. That was the kind of the point of this post. But still, you know, it's still less than 7 at every level. So it's really hairy and complex, but hey, you know, it's just a hierarchy of things less than 7. It's not so bad. So let's see if I can get back to my, there it is. So I don't know, it's just kind of interesting that you can build a classifier on just about anything, and just, you know, go in small chunks and just really make use of hierarchy. So I think one thing that suggests is kind of a CNN style architecture. You know, it suggests that, you know, at the bottom level, you know, you need a lot of let's say tokens, and then as you go up in layers, then it narrows. And so you, in the audio case, it's called dilated convolution. So for things like WaveNet, and it's, the classic is the CNN, right? It's the max pooling between layers of a deep learning convolutional neural network. So that sort of max pooling, that sort of sparsification, that seems like that should happen. But, you know, in a language model, you can imagine all sorts of other things going on there. I have a, just to remind us, you know, so this is the transformer. So here's a causal attention layer. So this, so this idea would be that if you know, start doing grouping, you don't really need as many states at the next, you don't need your sequence model to go from the same length to the same length. But we know that it's useful for other things. Like, for example, this first lane here that can only attend to itself. It has no past that it can look at. So the last one can look at everything. This first one can't look at anything but itself, basically. And so that's where the attention sink evolves, right? It's the most useless token, so let's use it for something else. And you get your attention sink in this lane. And who knows what else is going on in here. But really, if you're doing a classifier, you know, you only need one output, right? So you've got all this stuff coming in, and it's just that final output that says, well, here's what it is. You know, if it's a high enough level. So anyway, I think this is has interesting implications for analogies to max pooling in LLMs. I don't know if that's done, but it just seems like it makes sense. Let's see, how did I get here?
Can I jump in with a quick comment on that?
Please.
So there's no physical structure in an LLM like GPT-3 that looks like max pooling, but it is the case that when you do next token prediction, ultimately, all information needs to be coalesced in the last token.
Mm.
So while there's nothing physically that looks like that, inadvertently, when you think about it, if you have a bigger LLM and it has, let's say, 48 layers, what has to be true is that in the 48th layer, any information in tokens like 1 through second to last is completely useless. It serves no purpose at the present time. Okay. It's going to be there because the architecture is repeated at every token position, but fundamentally, that information is useless. Now, information in all those token positions at the second to last layer, the 47th layer, could still be used because attention can look all the way back. But you can imagine that there probably, practically speaking, are in fact patterns where attention tends not to go way too far back. And so you do kind of have a smaller receptive field at layers 2, 3. And then when those things are composed, you're sort of getting that bigger receptive field, and stuff is sort of, generally speaking, squashing until at the very last layer it has to all be in the last token position. But again, not physically enforced, but probably logically it does kind of look like that, now that you bring that up.
It also makes sense that if it doesn't have to squeeze it all down to one final thing, it might as well keep as many parallel theories going as possible, right? It could have various alternatives as to what might possibly be the answer. It's like a plurality of theories as to, you know, what the next prediction should be, and they could be very different paradigms, right? They could be according to very different initial assumptions, and so that might be a reason to keep them all going. So it's more like multi-head attention happening across tokens instead of, you know, like splitting up one token into multiple heads. It might be the similar thing. It seems like a good thing to look for.
Julius, I was going to just comment on something that I thought was just at a much higher level, kind of more abstractly funny, which is that if you look at the history.
The hiss? I heard nothing after S.
We lost your audio.
Work and does generalization really well, but we kind of hate that it does it in the CNN world. And in the context of a talk about DSP specifically, and I'm not a DSP expert, but I'll just share my perspective on DSP, that broadly, when I studied DSP, it's.
Uh-oh, we need you to repeat that.
Hey, Sally, you got a bad connection. Your audio is breaking up in and out. So we'll get you for like 3 or 4 seconds, and then unfortunately we lose you.
No. Ignoring me and continue. My connection's been great right up until I started talking. Anyway, I was just going to say that DSP is kind of like max pooling broadly, and that it's like magic, and the goal is to compress things in a way where the empirical results are good, whether we fully understand the underlying reasons, which is kind of like what you and Roger were talking about, is you're conflating memory with accuracy, or time with accuracy. As long as it works, kind of keep going. And that's kind of max pooling in a nutshell.
Yeah. It just seems like it's wasting computation, though. It seems like, you know, it just seems like it doesn't need all these, well, in the context of billions and billions of neurons, maybe it's a small point, but it motivates me to want to do ablation studies where I make a more pyramidal, well, what it actually would just look like an autoencoder if I did that, right? And that is kind of a classic thing. And it's sort of deprecated now, right? So BERT was like, you know, an encoder, you have a bottleneck, and then you decode on the other side. And so nobody's doing that anymore, right? Everybody's gone to pure autoregressive, and that's what this talk is about. Actually, it shows you the progression. So this is like a BERT style or a original transform. You have your bidirectional attention and your causal self-attention here, and they he took you through the steps of converting this into a pure autoregressive thing. And so you can see the transformations on that. So the
By
basic
the way,
idea
just
is,
super
yeah,
super quick comment, if I may.
yeah,
The all that computation you're talking about that's sort of towards the upper left, you know, uh, that's wasting flops perhaps, but it
yeah.
is not wasting parameters because the parameters are shared across all token
Ah,
positions. So the
uh-huh.
computational power is not like being wasted in that region, or you know what I mean? The whatever computational capability, but you're absolutely right. Flops are being consumed in all those other positions. So that might make it a little less wasteful than if it were actually like full on separate dedicated computation that's kind of going nowhere.
Ted, the other question I had about that, though, that's related to this is that I've often wondered how those activations at each of the layers, it's essentially the key value cache, right, that goes all the way across. Like how much of that is used to generate the current token, the token in that column, versus how much of it is used to be leveraged by later tokens? And is there some sort of waste of capacity or something in that I'm generating key value pairs that were really only used for that time frame that didn't help later? And if there was a way to separate those two concepts, I don't know.
I think the short answer is we know that it's sparse, but the problem is you can't predict the future, so you can't just eject a token and say, "Oh, we're never going to need this for future attention." You just don't know, right?
Yeah, I mean, this one, doesn't this token have completely independent, it has its own query vectors, right? But I guess all the key
Yeah.
vectors are the same across. I mean, there's a fixed sequence of key vectors along here, but each of these position gets its own query, and it
So,
dots with those keys and comes
but
up
kind of
with
what
that.
I'm getting at is that you have this very long text, and the first sentence is, uh, uh, "For Christmas, Alice got a pony." Okay, and then the next sentence is, "For Christmas, Betty got a zebra." I don't know, whatever. Um, and you just don't know whether 3 chapters from now someone is going to talk about how that was the best Christmas present ever for Alice, or they're going to talk about the best Christmas present ever for Betty, or if neither is ever going to be referenced ever again. You just don't know. And that's why the Transformer, you just keep everything. And then suddenly, 3 chapters later, if you see Alice was remembering fondly that Christmas, now all of a sudden, Pony may get the attention a gazillion tokens later, but you can't predict the future whether or not you'll need it. That people have tried.
Well, this gets back in a bit to Julius's associative memory that we were talking about. That you can choose not to put stuff into that memory or into that state. They may, it may or may not be important what Alice got, but the word "the" in that sentence probably wasn't important, right? And so it does feel like there's something where you can't. It's always best to have access to everything, but it feels like if you want to worry about the size of your key value cache, that you could be smarter about it somehow in a probabilistic way.
Yeah, and that's the hope and promise of these newer models like Mamba and whatnot, because they have finite memory capacity. So how are you, whatever your state dimension is, they're fine, right? So how are you going to remember enough for a sequence length of whatever, 64,000, 100,000, 500,000, million, 2 million? Like at some point, it has to be the case what you're saying, that you just get you get a saturation where you really don't need any more storage, because at this point 90% of what you've seen is thes and repetitive stuff and junk. And so no matter how long your sequence is, I can store everything that I've ever seen in this much capacity memory. So it's not going to be true in the limit, but if it's approximately true that for whatever we would call it, normal human text, you know, that the amount of new stuff gets smaller and smaller and smaller, and so that if as long as your memory is bigger than that, and you figure out the exact right way to track what to keep, what not to keep, then Mamba can store enough in for, you know, 1 million sequence length that it never needs to look back.
So I'd never heard it described that way, but that's really helpful way to think about it, is that by restricting the size of your context, you may gain these mechanisms that say, let me use the context more efficiently. Transformers have no restriction. They use up as much as they want. But these other techniques are saying, no, you got to limit it. So now a better model will use it more efficiently. That's cool.
Yep. Yeah. So by throwing gobs of compute at it, we found that we could devise algorithms that seem to do pretty well, right? GPT-4 works pretty darn well, but we just possibly have a very inefficient algorithm. So now people are searching for, is there something more efficient, but that gets us the same performance? And it's still very unclear. Things can compete at a small size, but whether, I haven't seen hardly anything published. So, you know, those RWKV and Mamba 2 and all these other things. And I don't know if it's because nobody has to compute, or if it's because anybody who ever got it to work is just trying to profit from it. And so they're not actually publishing their successes.
That, and then you combine it with the scaling laws that just say it'll do better if you have more. So it's cheap to buy more and become the best model on the block.
Yeah, but it's not getting cheap to buy more. You know, we've reached
We're
that
hitting the
point
limit.
where
Yeah,
that the graduate students can't do a lot of work they would like to do just because of the computational cost, translating to dollar cost, or however, whatever thing you want, resource cost now. So anyway, I'll just throw that out there. We should probably move on though, Julian. I think you have
I
some
like the
more.
next slide, Julius. Let's
Yeah.
go.
Yeah.
Okay. Yeah, I just thought I would throw this up here as a food for thought. So let's see, where are we? So I think we're at let's see, where are we? I'm going to just recapitulate a bit. Okay, so yeah, this is what we were doing. Yeah, so I was back here. So yeah, I just wanted to show you this calculation. Oh yeah, this is where we were. So just a thought experiment on hierarchy is making it possible to use quite short memory. So an RNN can have no problem at all holding, 7 digits, right? So, if your gating is good and you have a good reset, right? So it knows when it's done and it's starting over on something. So I just think that's a really interesting way of thinking about building things out of small memories. And so in the pictorial realm, you have 6 dots on a die. You have 7 LED segments for numbers. You draw a letter with 4 or fewer strokes. So, we can use hierarchy to keep the number of components per concept small. And so that means, you can have the memory resetting pretty frequently if it's just taking these small gulps, and you've got plenty of hierarchy for assembling everything together. But, to get back to the zebra and the pony, I mean, that's just got to be propagated up the layers. If you want zebra available, thinking about like needle in a haystack, I just don't even know. You just have to have all those needles in there. And so there's really no way out of that. There's no hierarchy that's going to help that, as far as I can, unless the needles are organized in some way. But if it's just a raw memory test, I don't see any hope there. So, that's a problem. I don't have an answer to that. But the hierarchical case where things make sense, that seems quite doable, and that's kind of what really matters the most to me is just language and understanding language and being able to parse and to form, a classification task. It's like a CNN. It's like image classification. You have edges at the bottom, and you start recognizing faces and shapes and textures come up. But the turning that into a prediction problem, and then getting conceptual frameworks that facilitate prediction, that's like way out there. I don't have a toy example of how that works, but I'm working on it. Okay, so these are the suggestions that come out of that we talked about. So anyway, so then this is just another extension. I'll just flash by this. This is the same kind of extension for the random sums to the decaying case, and instead of capital N, instead of little n over big N, in other words, instead of time over model dimension, we have this. So you replace time with this 1 over 1 minus pole squared, your forgetting factor squared. And so that's essentially the effective length of the exponential, you could say. And so it's kind of the same idea, but at least it's got a formula that you have control over with your feedback coefficient. And you can say things like, well, if I want my effective length to be less than the model dimension, then I just need my feedback coefficient to be less than square root of n minus 1 over n, the model dimension. And I can also have it be less than n over 2 by keeping it below square root of n minus 2 over n. So this is very easy. I mean, that's very, very close to 1. It's not a bad restriction, because this is the model dimension. It's at least thousands, if not hundreds of thousands. So that means we really can have a very long memory in an RNN. But another thing that's interesting to me is that I've never seen this formula for a guideline as to what your maximum feedback coefficient should be in an RNN. In Mamba, you have this offset that you can set to do that, right? So it's an exp of minus soft plus of parameter, and there's an epsilon that's added there, and that epsilon can be driven by this. This actually tells you what that epsilon needs to be, according to one way of thinking. So I don't know, signal processing making a suggestion. And we talked about this before. It's just a practical look at a bunch of model dimensions and vocabulary sizes and how they lay out. And I just thought that was very interesting. Okay, so this is so then what we did, we talked about making the vector memory, and then we decided, oh, we need to reset it. We need to have gating, and so that led to input gates and feedback gates and a number of suggestions. And we talked about the Mambo soft plus thing. And then we extended it to the skip connection, the gated RNN with skip connection, by just adding an output gate and having a really good idea of not scaling for power normalization, but to we had this discussion about not messing up the later layers, and so there's some interesting things there, because the whole idea is just to is 20/20 hindsight, trying to invent what we're doing in some principled way, so we didn't have to just stumble onto it. It's that kind of, because like I was saying, I would have had power normalization here, effectively 1 minus c squared here, but that's not what you want. You want to just leave it going straight across, because then you have a skip connection that goes unfettered all the way through, and it also means that your back propagation gradients get equally propagated to all of the layers. There's no way to mess them up. So that, and then you have the interpretation that you've got this residual stream, and these layers only get brought into the residual stream when they can actually help, and so that all works really well. So you have to have a lot of ideas really to get all that to come out like that. In other words, the signal processing suggestion there was not the best one, but you can at least still think of it. So that's not bad. Then we went to state expansion and got the state space model type things. Basically just the same thing, but now we're expanding the state because we want more model capacity. And I fixed that output matrix here. So this is your basic state space. It's just the skip connection thing with the state space expansion. So this is your expansion factor here. And so we talked about that. I think we covered all that. Okay, so then so then we covered all this, and we spent a lot of time on rope and And I looked for the rope lecture. I haven't found it. Is it online yet? I didn't find it. Anyway, so compressed time. So yeah, so it's time for attention, and I'm going to make it this time. So this is where I always ran out of time before this, and so now we're here. And so the basic idea is, the original was a one-pole filter. What can we do with that? Let's make an associative memory, and we just think of this as a vector memory. It's just an accumulating sum of vectors that come from an embedding, and then we can detect what's in here with the inner product. So this is our basic IIR filter, and when we extended it to state space, then we ended up with the most general IIR filter structure. And in fact, it's even more than that, because this C matrix here allows us to have an FIR part. And so now if you just get rid of the feedback, you have what we call an FIR filter. And the way that's more typically drawn is like this. So this is just a typical signal processing diagram for an FIR filter. And so your input comes in, it goes into a delay line. And then you have taps on the delay line, and you multiply those signals by coefficients and sum them up, and you get your output. And that's your FIR, your finite impulse response filter output. It's also called a transversal filter. And so now we can say, well, let's vectorize this, put an underbar under everything. And now these coefficients can be, they can be gates, right? So these can be learned coefficients. And so now we have the ability to learn a coefficient as a function of the position in the input delay line, as well as the output position. So this only shows one output, but there's a bunch of these, right? So that if it's a sequence model of, let's say M to M, we have M inputs here in our context buffer. This is our context buffer. Then there would be M outputs here as well. So this whole thing would get repeated, and it would make a big mess for me to draw that. So that this looks like a dot product here. So you really need a full matrix. So these C's here are essentially your attention matrix coefficients, and they're the dot product attention coefficients. So that's the so let's see if we can get there. So the idea is we have these learnable coefficients on these vectors going by in an FIR filter. So let's see what you can. Oh, and by the way, the context buffer is also the expanded state of the state space model. They're the same thing in this formulation. Okay, so we've got our input vector at position J in the context buffer. We have output position K. And so the idea is, let's add relevance gating. So we know how important gating is from our experience with the feedback associative memory thing. You got to gate unimportant inputs. You've got to reset the feedback. You even want to gate the output when the whole layer is not worth anything, and let the skip connection just take it to the next level. So the idea then is that we'll add the gates, and that's a component of attention. That's part of the story. And then we can also think in terms of creating new embedding vectors as sums of relevant input vectors, because in other words, we're forming this linear combination. And so we can think in terms of only choosing the relevant tokens coming out of this delay line, and we can choose them differently as a function of position. And what we form at the output, we can think of as some new thing that is, the attention sum, right? So when you add these vectors together, they mean something new. And so if you think in terms of the hypersphere, your vocabulary is a certain set of points on the hypersphere. When you add some related group of points, you get a new vector, which is presumably a totally new vector that's never used any other time for anything else. And so that would mean something like the word apple could become, could be added to, I don't know, pear and banana and get fruit basket. I don't know. You get the idea. In other words, nouns and their adjectives all combine to give you one vector that means that noun with those modifiers. They even talk about contextualized tokens. And so instead of just a token, you get a token in its context. Okay, so that's all common discussion in the attention world. So that's the way. That's a way of inventing this sort of thing. It's a start, right? So we're going to measure the relevance the same way we retrieve from the associative memory, which is by means of an inner product between the output and the input position. So that's our dot product attention. And so we need our relevance gating. So that means we're going to multiply the input by a learned vector. And so we can actually say what we're looking for. So we're getting to the query. So we're getting the query vector, and you can say that the query vector could be thought of as a sum of all of the tokens that we care about. In other words, we're at position J. Let's say, so we're computing the output Y. And so let's say we're looking at the contribution to the output CK3 here. So that's position 3 in the input. So then this query can say, well, if you have any nouns, I want you to add in here or something like that. And so this would then just be a sum of all the nouns. And then if any of the nouns are in position J, then you'll get a firing, right? So what the noun that's here will create a 1, and you'll get your vector. So it will only sum if the query vector contains in its sum the vector that you're retrieving or that you're gating. And so that's just one way to approach it. And so you've got a query vector, but still it's just applying to the token directly. There's no notion of key or value. And so I tried to think of how to come up with that. And I came up with a number of ideas, but I thought the best one was to just go to multi-head attention. So if you decide that you need that, then you get it right away. But for the query vector,
Julius,
yeah.
Can I ask a question?
Yeah.
So before you get to the keys, just looking at that equation that has like C in the subscripts on the left equals Q in the subscript times X. Yeah, that guy right there. So
Can't select it.
one of the things that makes attention powerful, but also expensive, is that in this diagram above, you can have things just be individual signals, but you put the underbar on it to show that it's now a vector, okay? And pretty much everywhere that you do anything in a transformer, like if you're calculating the C values, there's channel mixing happening. So if X is a vector of length 512, it's not that C1 is a function of X1 and C2 is a function of X2. Transformers do channel mixing where C1 is a function of every single one of the 512 X's. And that gives it a tremendous amount of expressive power, but then at also a cost. So I wasn't sure if in the signal processing world, this channel mixing business does or does not get used in various kinds of applications.
Well, when you say channel mixing, you mean the individual components of the vector?
Yeah.
Yeah. Well, I'm doing channel mixing here, but I'm doing it as part of the inner product. In other words, my query vector is going to be a dot product with the whole vector. So I'm going to take a linear combination of those channels because I'm thinking of it as a vector that I'm trying to recognize. It's just the same as the associative memory retrieval. So I don't think of it as channels. I think of it as just components of a vector.
Yeah, no, that's right. It's just that if your model dimension is 512, you have 512 of those Qs that you're dotting.
Yeah.
So that eventually your capital Q properly written becomes a 512 by 512 matrix, as opposed to it's just a vector, because it's a vector for X sub 1, and it's a vector for X sub 2, and it's also a vector for X sub 3, and so on and so forth.
That's
in the transformer.
Okay.
So that's again makes it super powerful, but also very expensive.
Okay.
right? So it's not the case that you have one Q vector, you multiply it by the entire X vector, and you get a scalar. That would only give you one scalar. You need one scalar for each of the 512 components of X.
So, well, now I do have more outputs. In other words, this is only one vector here, but when you list out all of the outputs, then it does become a matrix. But it is true that I'm only, doing one dot product
Right.
per output.
Yeah, I think if I'm understanding your analogy, at attention for any given token position, we are actually doing n dot products with in order to calculate our query.
Well, I do need to go review this because I'm really only thinking of M, not N. In other words, I only have M dot products in this formulation. So the only way I can get it up to capital N is if I have the same number of my context buffer length would have to be equal to the model dimension. That would give it, but otherwise I have much less. So I would normally have much less than that. Okay, so I'm going to review that because, yeah, I have no way to suggest, going to that level. Although I guess one way to suggest it is you just want that many queries, right? So each row of that is a query, and you can just have 512 queries for each token, and so yeah, you get a lot of expressive power from that. So
Yep.
yeah, I'm not there yet. So I don't have that yet.
Okay.
I'll work on that. Okay, but here's how much I do have. So right now with my one query vector per token per output, I'm able to get my relevance gating, and you can form the query as a sum of things that you're looking for in the same way that we were using a query to retrieve from the associative memory. And so to me, that's very satisfying because I can take my input vector, multiply by this query vector, and if anything I'm looking for is in there, if it's any of these, basically, then the dot product will be 1, and so that'll let it through. So it's a gate where it says, I only want this input if it's one of these. And so that gets you, one kind of query mechanism, but you're still just using the original token vector, both for the key and for the value. And so I did think of a few ways to, you can just think in terms of generalizing in various ways. But to me, when I don't know about you, but when I read the Transformer paper, I was really surprised. I mean, I hadn't been, reading language translation at all. I didn't know anything leading up. This is really when I got started on this stuff. I just, as a signal processing diagram, I was just blown away by how many things I didn't expect, how many things I didn't see coming, you know what I mean? And the fact that you're willing to learn these query matrices and key matrices and value matrices, that just seems so over the top to me. I just really needed some reason to feel like that's reasonable, and that, yes, I want to train all that stuff. And so my favorite description, or my favorite motivation, is just simply multi-head attention. And that's a very simple, straightforward idea. It's like you want to support multiple meaning possibilities. So we don't want to commit to just one theory of what's going on. We want multiple theories of what's going on. So we have we partition the space, and we have parallel independent attention calculations. So that's multi-head attention. And so since we're carving up the space, we're going to have to adapt to it. And it's those adapters that give you that's one way to get the key and the value vectors or matrices. So each attention head can do an independent input interpretation. And this makes a lot of sense for ambiguity. And you can imagine in the lower levels, you're always going to have a very ambiguous set of possibilities as you're just getting started in the layers. And so that was in the transformer paper. So you get your key and value matrices immediately by just noting that you got to down project. So you got to go from the full space, full model space, down to the partition for the attention heads. And so so that takes your relevance gate to this form. And now we've got the except that we're missing 511 rows. But at least in the single row case, I'm satisfied that, yeah, this has to happen, and I've got an interpretation that makes sense. And so now we've got query key and value, and we down project from the input to the partition, to the spatial partition for the attention head, and off it goes. And so we end up with a lot of we've got a new index here for attention head. So that, I thought that was nice because it's pretty unavoidable once you want to do the multi-head attention partition. Let's see. Oh yeah, and some of these other generalizations that I was thinking about were like, once you have these, you can do things like grouping grammatical functions. So you can say, give me all your nouns, give me all your verbs. If you're working on a noun and you just want all the adjectives, that might modify it. You can imagine query, and I'm sure this is studied. I'm not an expert on this stuff. I bet this is well known by now that that kind of thing goes on. And you can also use it to fork off into new regions of the model space to kind of spread things out. So there are a lot of things you can do with all this extra freedom. So now it's time for the grand unification of transformers and gated RNNs. And so this sort of harkens back to the state space formulation where you have this feedback matrix A sub t. So for the transformer, it looks like this. It's just a shift. And so and I'll go ahead and throw in the rope for positional encoding. And so an input comes in on the top and it gets shifted down. And that's just your FIR filter case. And then the state transition matrix for Mamba, for an RNN, is a diagonal matrix, and it can also have rope. They don't usually do this actually, but you can put it in if you want. And then of course you also have your forgetting factor that is a function of the input. And so it's similar to Mamba 2 or regular Mamba. There's not that much difference between them. So, you have your transformer, you have your RNN, and they're both state transition matrices. You can combine them. So here they are in one big matrix. So this is just one big state space model, and it's got a transformer section up here. And here's the input matrix in the state space world. So you've got your gating matrix on the input here. And then the input comes in on the top row and it gets shifted down. So this is just implementing that FIR filter part. And then when you're going off the end of the FIR filter part, you have a set of coefficients that fire it into the RNN. And then the RNN section is just this diagonal matrix here. So that's your diagonal feedback matrix. And here's a diagram that illustrates it for a state expansion factor of 2 for the RNN part, and then a large FIR part, much larger than 2 anyway. And so the FIR part's first, and then the Mamba part is second, and you could argue about which order they should be in. And we talked about this a little bit last time, but the coefficients, this is the FIR part, we've talked about it, and this is a couple of RNNs because of is 2 because of the state expansion factor of 2. And then you can think about how you want to combine them. So the output will take the output of the RNN, and then it would also take some coefficient times the attention output, basically. And this is, of course, just one output of many. And so Mamba formula is taken, so I thought Trans-Mamba would be the only thing. But of course, I had to go into Mid-Journey and see what it would say for Trans-Mamba, and there it is. I actually think this is really, really nice. It has a, let's see.
Are you patenting Trans-Mamba now?
No, it's MIT license. You can do anything you want.
Okay.
Go ahead and take it. But
Thanks.
but this is mid-journey, first try. Okay, I just said for the first prompt, I said a friendly cartoon snake, and it gave me a boring cartoon snake. And then I said, okay, make it trans. And this is what it did. And I got the rainbow hair, I got eyelashes, I got earrings and necklace and a trans species brassiere. I mean, I was really impressed with Midjourney. I really was. So this stuff really does work. So let's see, where is it now? Okay, so then finally, this is my last slide, I think. Do we do direct form 1 or direct form 2? So in signal processing, direct form 1 is where you have your FIR part and then your feedback part. That is what we just looked at. It kind of makes sense, I think. But you could also consider direct form 2, and that's here, where you just interchange the order. So you have your feedback part followed by your FIR part. And so in this case, the FIR part does not delay the states. So in this case, your RNN is getting the output of the context buffer. So it's only for it's in some sort of automatic mode. So this is your normal transformer part, and it's only when the input would fall off the end that it goes into the RNN. So it's more for long-term memory. So you can say in this sort of thing that you have perfect short-term memory in the transformer, but then you go into the RNN and have a fuzzy fading long-term memory. And this is very much like infinity attention, where it's putting the KB cache out there in an RNN kind of structure. Whereas in this direct form 2 case, you have a fading short-term memory coming up, but you could also use this as short-term memory. But it seems like it would be interesting to think of this as a fading short-term memory and a limited, very definite long-term memory. And I do think that's also like the brain, because you can imagine, you're going along and you got a bunch of things in your short-term memory, they're fading. But if you see something really important, you want to recognize that. And so over here, you have the ability to recognize, oh, that's a spider, or that's a snake, or, just things that you don't want to forget. And when you see that over here, then you send a projection to the limbic system and get a reaction. So I think maybe it makes sense to use them both. So this is how far I could push signal processing 101 to get these structures. And so thanks for your attention.
That was impressive, my friend.